So hello everyone, and thank you for coming to our third event of the DSC month. Today we have with us Emily Williams, and she's going to present an intro to blockchain and DeFi. And yeah, so Emily, you can take it on from here. Thank you.
Cool, I'll take it away. Yeah, my name is Emily. I have been a developer in the Ethereum space mostly for about 3 years. I currently work at Uniswap Labs, and we make the Uniswap protocol. I've worked there for about a month, so I'm still pretty new, but it's been really fun. Before that, I worked at a company called Suma, doing some chain interoperability. But other than that, mostly doing Ethereum smart contract work. So today I'm going to give a pretty general and broad talk about what is blockchain and also what is DeFi, which is built on top of blockchain. And from a developer's perspective, so it will be a little bit technical. Yeah, so let's get started. So yeah, first, I guess, what is a blockchain? I'm sure if you're here, you might have an idea of what one is or have heard lots of different explanations. It's such a big thing that it might be described in many different ways depending on who you're talking to. But here I decided to define it as a distributed peer-to-peer network of computers that can trustlessly reach consensus when reading and writing to a shared data ledger, or it's kind of like a shared database in a way that kind of moves through time as transactions get made. And so what I mean by trustlessly is it's a way to maintain the shared source of truth with a network. And the network is secured cryptographically, so you know that other nodes in this peer-to-peer network cannot go in and write things to the shared ledger that that don't follow the rules or or aren't coded into the protocol. Yeah, and I think this differs from a lot of traditional technologies and databases. Like Facebook or big tech, for instance. In the traditional structures, there is an entity or a company that has a database or the source of truth. And a lot of us use Facebook and we read and write to Facebook. We send our data there and pull data from their database. But we don't really know how their code works, how things are written to the database. And if Facebook wanted to change things or censor things, it's very easy for them or any big tech company like Twitter or Amazon or even a bank. They kind of have the authority to go change whatever they want or delete things that they don't want. But with blockchain, there's no way to delete things from the database or change the database that's outside from the codified rules. So it's a way that we can all create a database in a decentralized peer-to-peer way where we know no one has the power or authority to change things. It's sort of like commonly maintained through cryptography. Yeah, and I think with blockchain, I think a big part of it is it's information that that communicates a store of value or money. So for the most part, when we think of blockchain, we think of Bitcoin or Ethereum, and these ledgers have information about the amount of value that someone owes. And so I think you can think of it as a huge disruption, not only in how we maintain data together as a society in the traditional sense where there's companies who have the authority to kind of maintain them how they want, but it's also a way to kind of share or decentralize how we kind of want to have monetary policy. You can sort of say that Bitcoin has its own unique monetary policy that the protocol follows, and Ethereum is different. And so it's kind of a way to decentralize that kind of power and authority. So not only is it different from maybe a big tech company, but also you can think of it as an alternative way to manage money from a central bank. Like in the United States, our president appoints the chair of the Federal Reserve, and they dictate our monetary policy to keep the dollar healthy. They kind of, maybe have a little bit of monopoly on money. But with blockchain, it's a database, and it also has like a protocol and a code that kind of codifies certain monetary policies that are commonly maintained through the peer-to-peer network. It's transparent. We know exactly how Bitcoin is going to work now. We know exactly how it's going to work 10 or 20 years from now. So it's another way, not only to have a database, but also it gets into the realm of money and how do we want our money to be structured. And it kind of gives us this opt-in power to opt into Ethereum or Bitcoin or whatever we see as the most viable option for us. Obviously, the technology isn't quite there yet to be super sound money. There's still a lot of things to work out, especially with the volatility. But yeah, anyway, so those are some of the whys. So yeah, it's a distributed peer-to-peer network of computers that can trustlessly reach consensus when reading and writing to a shared ledger. A blockchain combines a few technologies. One we've talked about is a peer-to-peer network. We have a bunch of nodes in a blockchain that help run the system. When we send transactions to and from the system, we'll talk to a node who will share the transaction around to other nodes, and they kind of work together to create blocks based on all of the transactions. You can see like each block has a number of transactions in it. And another technology it combines is private public key cryptography. So in order to transact with the network, you have a private key that is associated with an address. And so as long as you have that private key, you can sign a message that says, this is my address, these are the assets I hold, and I want to exchange them, or I want to transact. And it sees that you signed with your private key. And so these nodes know, yeah, this is valid. This is also really cool and different from traditional systems, because when we hold our money in a bank, really the bank holds that money, which is great, and that works, and it's pretty safe for the most part. But basically, when you spend your money, you're telling the bank, hey, can I please spend some of my money, or will you please hold on to this? But with public-private key cryptography, you're talking directly to the network with your private key, and so no one ever has control over your funds. You are the only person. You don't ask permission to send them, and no one's holding them. And I think that's really empowering and cool. The other side of that is it can be hard for new users or even really experienced users to maintain their private key, because if you lose your private key, you will lose all access to your funds. Or if you accidentally share it and someone sees it, then they have all access to your funds, and so you will lose them. And that's a lot of pressure for people, and to hold something like that, especially if it has your life savings on it. So that's a big problem that developers and the blockchain ecosystem is dealing with, is how to make people comfortable with something like a private key or different architectures to make it less make it less like losable, right? There's multi-signature wallets and different solutions to that. So yeah, we have a peer-to-peer network, public-private key cryptography, and the last thing is proof of work. And basically, we have all these nodes that share transactions and help produce blocks together. But it would be very bad if a node could push tons of malicious blocks, maybe with data saying transactions happened, but they weren't signed by the right person, or double spending money that's not there. And if there's too much spam in the network, it will ultimately break the network for reasons that I won't really get into. But proof of work makes it very expensive to produce blocks. And so it makes it expensive. So if you produce a block that's malicious and it's going to get rejected and it was very expensive, it's just not worth it to try and spam the network. So yeah, proof of work, computers need to solve the way it's expensive for these nodes to produce blocks is computers need to solve an extremely difficult computation to produce or mine the block. And this computation in cryptography is called a trapdoor function. It's very hard to solve, but very easy to verify. And so an example of a trapdoor function is if I have two large prime numbers and I multiply them together, I get a result. That's easy. But in the other direction, if I have a large number and I know two prime numbers go into it, its prime factorization is very hard. It's very difficult to find those prime numbers. But once they're found, I can go, yep, this times this equals this. And that's how the blocks kind of verify, yes, you did it, you solved the puzzle, and you produced the block. So this makes it very expensive to produce malicious blocks that will only get rejected by the network because computers need to expend a lot of electricity to solve these hard problems to make the block. So it becomes extremely expensive to cheat and spam the network. And with proof of work, basically what it is the hard function is you have to take relevant information from the block and you have to hash it with a nonce. But the result has to begin with a lot of zeros. So you keep hashing the relevant information against different random numbers until you finally get those zeros. And then that will be a valid block and the network will accept it. So if it's a malicious block, you did all that work, it has bad information, the other nodes do that, it's rejected, and you lost a lot of money. Ethereum is going to do things differently. When you hear people say that blockchain is bad for the environment, they are talking about this proof of work or these computers doing these hard puzzles that make it hard to spam the network. So what Ethereum and other blockchains are doing is they're doing proof of stake to address the electricity wastefulness issue. And with proof of stake, block producers stake value, and if the network detects a malicious block from this block producer, their stake gets slashed. So when Ethereum 2.0 comes out, it's not ready yet, but when they do release it, if you want to be a block producer, you need to stake 32 ETH, I believe. So that's, I think, almost like $60,000. So if you make a malicious block, you will lose all that $60,000. So this makes it expensive to produce malicious blocks that will only get rejected by the network. That way we, do away with spam that can break the network. Cool. So that's kind of what I'm going to say about blockchain. You could obviously talk probably for 10 hours about how all that works, but hopefully that gives you a good idea. So why blockchain? It's immutable, it's extremely secure, it's tamper-proof source of historical truth. The blocks get kind of appended on top of each other over time, and you can never delete what happened. So you can feel secure with your stored value being on there, that it will always be there and it will never be erased, and no one will ever be able to spend it without your private key. It's censorship resistant. There's no intermediary or middleman to restrict access. This can be good for more developing nations where access to banks aren't extremely easy and you want a safe way to store value. Even in the United States, I don't think women could take out credit by themselves until the 1960s. And so with blockchain, there can be no discrimination. As long as you have internet access, you can use the blockchain like anyone else, and you can seamlessly send money anywhere across the world. Borders don't exist with blockchain. Some governments don't like that because they believe sanctions is a good way to kind of gain an edge in the world when you need to maybe have power over someone. But blockchain makes that a lot more difficult. And it's transparent. The inner workings are auditable by anyone. Unlike modern financial institutions, it's very hard to know what's going on in there. Or inside the big tech we use, we don't really know what's going on behind the scenes. Blockchain is open source and transparent. Yeah, so those are some benefits. Yeah. And then kind of what a traditional web app versus a Web3 blockchain app might look like. It's very basic. But yeah, like I said, you know, in a traditional app, the bank or Facebook kind of has this database that we all talk to, but it's a black box and they dictate how they want to use it. With blockchain, it's a decentralized system of nodes that help maintain the network, that you know, follow the rules that were codified into it, that we all can see and know that nothing malicious is happening. It hasn't yet, you know, Bitcoin and Ethereum after years have not been able to be broken. And so a web app might talk to any different number of nodes. In Ethereum specifically, a very popular service is Infura. And that is a huge node run by consensus that allows people to read and write to it for a small fee. Sometimes Bitcoiners might complain that they feel that Ethereum isn't decentralized enough. And that's because, or one of the biggest reasons is because so many apps use Infura as their node. And so if Infura were to go away or be malicious somehow, that could definitely be a big single point of failure. And a web application needs to connect to a wallet. So instead of like a session ID, you might use in a web app to log into Facebook. With Ethereum apps, you might have a MetaMask wallet in your Chrome extension or your browser extension that helps sign messages for you with your private key. It keeps your private key safe. And we have a few JavaScript libraries like Ethers.js and Web3.js that can talk to wallets for you and also signal to nodes for you and help you with JavaScript sort of format those transactions to happen. Yes. So what is DeFi? So since I work in Ethereum, a lot of the blockchain work I do is DeFi, which is decentralized finance. Ethereum smart contracts make it possible to deploy financial instruments to the Ethereum blockchain. So with Bitcoin, when people think about use cases for Bitcoin, it's mostly I have money in my wallet and I want to send it to this wallet. It's just kind of payments back and forth to different addresses. For the most part, there's a couple, you know, there's other things that can happen there too, for sure. But Ethereum really tries to be this very big multi-purpose platform. You can code anything onto it with a smart contract. So it's not just, you know, sending to and from addresses. There's a lot more. So in order to paint a better picture of DeFi, I thought we could just talk about some of the popular DeFi applications. Obviously, these are just a handful, but to think of the stuff that's going on in Ethereum, things have definitely went in the direction of building financial instruments, which makes a lot of sense since these platforms have a lot to do with money. It's not the only thing you can do, but it's definitely where we're headed right now. So let's talk about some of the popular DeFi apps to get an idea of what that landscape looks like. So I want to start with a DAI, and DAI is a stable coin. So it is an ERC20 token. I know there was a workshop this week about ERC20 tokens, but you know, like Bitcoin kind of has one currency on it. With Ethereum, you can code your own currency on it. And as long as it follows the ERC20 standard interface, it will be compatible with all the applications that take currency. So DAI is a stable coin, which means the price hardly fluctuates against the US dollar. And this offers a way to hold value on chain without volatility. The price of Ethereum is always moving up and down, Bitcoin, all these tokens. So stablecoin is a really big concept to address that. Because like going from fiat to on-chain is kind of difficult. It's not decentralized. You have to go through an institution that can accept US dollars legally and give you an on-chain asset. And so that can be a lot of friction. And so if you want to kind of stay on chain but not deal with the volatility, you can hold a stablecoin. Another DeFi app is Compound, and this is a lending protocol, so you can earn interest on your capital. And that's like in the real world, right? If you hold a lot of money, a lot of the times we invest it and earn interest on it instead of leaving it idle, especially because of inflation. So what Compound does is it offers a way to do this with your on-chain assets. So on the other side of that, it's also a borrowing platform. You can also borrow tokens and pay the fees, which will be interest for other people, and pay the fees to borrow tokens. In order to borrow, it needs to be fully collateralized. So if I have DAI and I want to borrow ETH is worth like 2,000 DAI. So I'd have to give the protocol 2,000 DAI, maybe 2,500 DAI to borrow 2,000 DAI worth of ETH. So they're fully collateralized loans right now. But this is a way to earn interest. Another popular DeFi app is Synthetics. It has a few competitors, UMA, but they're derivatives trading on Ethereum. So you can hold synthetic assets whose price movement mimics off-chain assets like Bitcoin or US dollar or other commodities. You know, you can grain, oil. Yeah, so they're synthetic assets. So the protocol makes sure that these ERC20s are copying the price movements of off-chain entities. Then there's an app called Pool Together, which you can submit your assets into this raffle type system. So you can put your money into Pool Together with lots of other people, right? And then it puts that money into something like Compound to earn interest. And then at the end of the week, one address that entered their money gets all the interest from all the funds. So it's kind of like a big raffle on things like Compound where you earn interest. I had some money in Pool Together, but it's like the more money you have in there, the more tickets you bought and the higher probability you have of winning. And I put such a small amount in that I'm never going to win. So I kind of feel like I should have just put it directly in Compound or something. But yeah, that's the point. And then there's Uniswap. Uniswap is a decentralized exchange. There's also a lot of other ones. And so it's an automated market maker. You can programmatically trade tokens immediately without a broker. So if I have a ton of DAI and I want Ether, Uniswap would have a DAI Ether pool, and then I can submit Ether to get DAI. In the real world with real assets, if you want to do this, there kind of needs to be a person as an intermediary. Like if I have a ton of US dollar, but I want to buy Chinese yen, I need to find someone who can facilitate that for me that has that liquidity. With Uniswap, there is no person in the middle. It's programmatic and there's pools. So basically, there'll be a pool with lots of Ether and lots of DAI. And so the price of Ether right now is 2,000 DAI, more or less. And so say I wanted more Ether, I could put DAI into the pool, and then it will give me the equivalent amount of Ether. And as people put stuff in and out of the pool and give and take, depending on the ratio of the two ERC20 tokens, the price will change depending on that ratio. And so it's completely programmatic and there doesn't need to be a person in the middle, although there does need to be a lot of money in there in order to give and take. So you can also be a liquidity provider for Uniswap. If the price is 2,000 DAI to ETH, I can go in and just submit 1 DAI and 2,000 ETH, or 2 DAI and 4,000, or I'm sorry, 2 ETH and 4,000 DAI, and then leave it. And as people trade on it, I can earn some fees. Yeah, so if you have assets on the Ethereum blockchain and you want to kind of make more interest on those assets, you might look at all these things going on and say, maybe I will hold my idle assets on Compound, or maybe I'll be a liquidity provider on Uniswap, put my tokens in Pool Together. So I think there's just a lot of people a lot of crypto whales. A whale is someone who has a large amount of assets on the blockchain. And there's even a lot of bots. You know, a lot of these big whales will run automatic robots that are looking around on chain for the highest yield and might put the money in compound or synthetics or be a liquidity provider on Uniswap. It's just really kicking off this sort of financial world of managing money on chain. Yeah, so maybe you guys all have questions, but that's kind of a lot. But that's some of the stuff that is going on. Cool. So what does DeFi make possible? So all the previous reasons we talked about, it's immutable, inclusive, and transparent finance. A lot of these financial instruments aren't readily available to a lot of people, but if you have access to Ethereum, now you can do all that stuff we just talked about and manage your money, which is really cool. There's a concept, a very specific concept that I thought I'd touch on, which is flash loans, because I think flash loans are really cool because it's something that has only been possible since DeFi. Doing a flash loan was never possible in the traditional world. And we've seen them happen a lot, and actually people have performed very cool attacks with them. But what a flash loan is you can borrow, excuse me, you can borrow large sums of money and pay it back all in the same transaction, since each transaction has exclusive access to chain state for the duration of the transaction. So when we talk about, you know, as we send transactions to the blockchain, the block producers take them and incorporate them into the block. They, you know, do the operation as long as you sign with your private key. And these transactions are done one at a time. They are synchronous. So as the nodes collect the transactions, they run through them one at a time, which means that when your transaction gets run, it might be a small transaction. Maybe you're just sending money to a friend, or it might be a large transaction. You might, all in one transaction, take money from Uniswap, invest it in Compound, and do a couple other things. You can really jam pack whatever you want into a transaction. And so with a flash loan, what you can do, I think Uniswap allows this, and Aave, a lot of protocols, I can take all liquidity from a Uniswap pool, just take it all out. And then I can do whatever I want with it. And as long as at the end of the transaction, I pay it back, everything was valid. And what this allows is people without capital to do capital intensive transactions. And an example of that is arbitrage. Now in arbitrage, it means something might sell for cheap somewhere and expensive somewhere else. So for instance, if the US dollar is really expensive in Mexico, but really cheap in China, I could go buy a ton of US dollars in China for cheap and sell them very expensive in Mexico, and I can take the difference. That's arbitrage. But in the real world, you need a lot of money to buy all those assets in order to sell them. So with the flash loan, as long as I borrow money and pay it back in the same transaction, I no longer need to be rich. I can borrow some money really quick, do some stuff with it. Maybe I made some money off of arbitrage or whatever I did. I pay it back at the end. And as long as I pay it back, the transaction is valid. Ethereum transactions are all or nothing. So if I'm performing a transaction and finally it errors out, everything will get reverted and the transaction just gets thrown out. So with a flash loan, if I do the whole transaction, but at the end I go to pay it back and it's not all there, everything gets reverted and it gets undone. So I think that's a cool example of something that is possible on DeFi that was never really possible before. Yeah, and other than that, we have open finance, a lot of really great things that we talked about that blockchain just provides natively. What are some DeFi challenges? Lots and lots of challenges. The challenges slide was a lot easier to make than the possibilities slide. So here's just a few things of many, many things. So identity-based transactions. there's no concept of identity on the blockchain. It is a private key and a public key that kind of dictates your identity. So lending or granting credit typically involves reputation and accountability. So, in the real world, if I want a loan for a business, I need to go through a process to make sure that I can pay it back or have collateral. On the blockchain, you can't do that. If people give out money without the promise of being paid back, everyone would just take it. People would take advantage of that and take money and never give it back. So it's not possible. And also, Sybil attacks make it very difficult to do identity-based voting or governance. So a Sybil attack is when you pretend to be more than one person. So you can't do one vote, one person, because I could just go and make 100 accounts, get 100 private public key pairs, and pretend like I'm all different people. And there's no way, or it's very difficult to verify someone as a real person. So we can't do things like one person, one vote. Front running. So yeah, miners and bots can monitor transactions in the mempool and compete to complete profitable transactions before the original transactor has the chance. So we say we all send our transactions to the peer-to-peer distributed system, all the nodes, and they share the transactions with each other to get processed. So those transactions are public. Everyone can see them, and everyone can see what you plan to do. And so bots look around and try and find someone that's making a profitable transaction and make it before them. So an example might be, if you send tokens to a Uniswap pool by accident, and now there's extra currency floating around in that contract that's outside the scope of the protocol, anyone can come and kind of take it out because it's extra money floating around in that contract that doesn't need to be there. It's just how Uniswap's coded v2. So if I did that by accident and I sent a lot of money there and I'm like, oh no, I need to go get that back. So if you made a transaction to go get it back, people looking at the mempool, and especially these are bots, they would see that, and then what they would do is they would pay a high fee to get their transaction in first and take it before you have the opportunity. It does cost a fee to perform a transaction on Ethereum, and larger transactions are more expensive than smaller transactions. But you can offer any fee price. So if you pay a higher fee, it will get incorporated faster, and lower fees, it will lag. So what these bots can do is pay high fees to beat people in transactions where they know they'll make a lot of money. And there's a lot of different ways that bots are looking around to kind of take out value where they can that might otherwise go to a normal everyday person. So it's a big problem, and there's solutions that people are thinking of to it, but that would be a different talk. And another challenge is incorporating off-chain information. So designing trustless oracles to relay off-chain information is still a challenge. Examples: stablecoins must know the value of $1 to remain pegged to the dollar. Or if on the blockchain you bet on a sports team, knowledge of the winning team must be relayed on chain. So you kind of need to trust someone outside to come on and say, oh, this basketball team won, or oh, the dollar right now costs this much Ether. And so when we talk about trustless, right, within the blockchain world, we don't like to trust other people. We like secure cryptography where we don't need to trust anyone because it's impossible to cheat. So with getting off-chain information on-chain, there's a lot of solutions. Chainlink is a big company that offers oracles, but getting that information on-chain in a way where we don't need to trust whoever is submitting it is a challenge. For stablecoins, I think a popular thing that they do is they consult big exchanges like Coinbase or Binance and get the price from there and transmit it on chain. But it's easy to cheat that. So that's definitely a big challenge. And there's a lot of challenges, but here's 3. And then more specific developer challenges. As an Ethereum developer, there is a massive need for efficiency. So we said that larger transactions are more expensive than smaller transactions, and it's because every single computation costs gas, and gas is, is kind of like the amount you're paying per computation. And so when you break your computation down into assembly, right, every little piece of assembly costs a little bit of money. And also every piece of storage costs gas. Every time you want to store something on the chain, that means that has to go in, that needs to go into the memory of every single node or computer around the world that's keeping track of the chain, and that adds up. So it's expensive to hold information on there. So as blockchain developers, we have to minimize on-chain logic as much as possible. And we need to store data as primitively as possible. We have to get it very small, and people are always working to do that. What time is it? Okay, we're doing good. I'm almost done. But an example of getting super efficient is a contract, which I link to, and you guys will get the slides, is a Merkle tree token distribution. Uniswap was the first to do this, and a lot of other teams have copied this pattern. So with Merkle tree token distribution, what Uniswap wanted to do was give a token to all of their users who had used the platform in the past, to every address, right? We don't know individual people that have used it, but we can see every private public key pair that has transacted with Uniswap. And they wanted to give a token to all of these past users. So it would be very expensive for Uniswap to do the transfer for each one, because those transfers would add up to tens of thousands of people. They wanted people to be able to make a transaction to pull their funds. But to store all the information on chain of what address is owed how much money, that would be a lot of storage, and that would be extremely expensive. So what Uniswap did is they used a cryptographic primitive called the Merkle tree to get all this information about tens of thousands of addresses and what they're owed, and they put them in the leaves of a Merkle tree and hashed them up into the Merkle root, which is no more than 256 bits, very small. So some of your computer science, you're studying that at school, so I guess I won't go too into the Merkle tree, but basically, every leaf node was an address and an amount, and then they get hashed together to make, a random string, and things get hashed together all the way up to the tree until the last 2 layers get hashed into the root. And so if you wanted to pull your funds, what you had to do, you could go to the Uniswap website, and depending on your wallet, you connect to the app, and they see what your private public key pair is. They only see your public key, right? They don't know your private key, but they know your address, public key. And they can say, oh, based on this address, you're owed this much. And so off chain, they give you the proof, they give you what you're owed, and you put that on chain. You call a smart contract and give them all this information, and the smart contract takes the proof, takes your amount, and then does all the hashing and can see, yep, this matches our root. You are owed this amount of money. You've proved it. Here, you can pull the money. So that's a lot of off-chain information that got condensed into something very small on-chain that we can query with a proof we've computated off-chain. And so it was like 256-bit storage, super easy, everyone can pull. I just think that's a really great, clever example of how we minimize our on-chain logic and maximize what we can off-chain, just because it's expensive. And also because in my next point, bugs are expensive. If some contracts get hacked, people will drain millions of dollars out of them, and it's happened. in the real world, you can kind of reverse that. Banks have insurance on chain. Things are a lot different. That money would be gone. So you really need to do is minimize the complexity of your on-chain logic. This not only makes it cheaper to store logic on chain, but harder to hack because the code is as simple as possible. Professional code audits are crucial, and they're also very expensive. You need professional code reviewers to make sure that you don't have a bug that's going to drain millions of dollars. It's very high pressure to deploy code to Ethereum mainnet and know that there will be millions of dollars in there. It's pretty scary. Yeah, so those are some of the challenges that we deal with. Yeah, and I just slapped the slide at the end. Some other interesting things going on is scalability. Like we said, it's really expensive to store things on chain. It costs gas. Gas prices have been really expensive. Lately, it's been very expensive to perform transactions on Ethereum. So to make it more scalable, I talked about proof of stake instead of proof of work. Ethereum's doing something called sharding, where there'll kind of be multiple chains that sort of talk to each other. I can't explain that very well, honestly. And then layer 2. It's interesting to delve into layer 2, which is basically using, you do a lot of off-chain, but still cryptographically secure transactions. And then you might checkpoint, all those transactions might get rolled up cryptographically to do something small on chain, kind of like that Merkle tree that we talked about. You kind of send hashes of bigger things that have happened. And these are called roll-ups. So layer 2 is going to be a big thing happening to make Ethereum cheaper and faster. Ethereum isn't the only chain. There's other chains that are doing proof of stake and roll-ups. But since I work in the Ethereum space, I focused on that during this talk. And I think that's it. If you're interested in learning more about doing any sort of Ethereum development, I recommend Crypto Zombie's Solidity tutorial. Twitter is also a place where lots of conversation happens. Lots of stuff happens on Twitter. Lots of ideas get thrown around. It's a huge hub of communication. So these 2 links are a couple of lists. One that I made of just people in the space that I follow. Another one is someone I know made. So that could be a place to get started, to start kind of following people who have interesting things to say in the space. And Reddit, I think ETHDev is a great Reddit subreddit. The other ones can get a little spammy and too much talk about price and investing, but ETHDev is a great place for more technical conversation. Yeah, and I guess that's it. That's my talk. Thank you.
Thank you. So if anyone has any questions now, just feel free to unmute yourselves or write something in the chat. And I was personally going to ask about the 2 things. First, the flash loans. I know there's been certain attacks using them, like you've mentioned. Do you know of any example that's easy to explain? Because anytime I've tried to look into it, it's very complex and I haven't really understood it 100%.
Yeah, geez, I haven't looked at some in a while, and I feel like they do get a little complex. So when I do look at one and then a few weeks have gone by since I've thought about it, it's kind of whoa. And I sort of off the top of my head, I don't really feel like I'd be able to explain a specific attack that's happened really well so that people could really understand it. But I feel like I could definitely follow up with some blog posts. But I think one of the big reasons that it allows these attacks to happen is because for a lot of attacks, you need massive amounts of money to pull in and out of protocols to start messing with the bugs, so it just takes a lot of value being moved back and forth to create big bugs. And so without flash loans, you would need to be very rich to be able to perform these kinds of attacks. But with flash loans, because all of a sudden you can get all this capital at your fingertips, you can start moving it around and really messing stuff up. And so that's why flash loans make attacks really easy. It's just because you don't need the capital anymore. It's, it's not easy to be rich, right? Or else we'd all be rich. But now you have access to capital to move a ton around in order to manipulate different bugs. But I can definitely follow up with maybe more like, I think that could actually just be an interesting talk in and of itself. This talk was really broad, and I think more interesting talks get a little bit more pointed, and I think like just going through an attack would definitely be an extremely interesting talk. But yeah, I don't really have like a super detailed explanation of one off the top of my head, unfortunately.
I mean, I think a talk about that would be interesting, and I guess it does make sense, right? If you're moving huge amounts of money, maybe you can impact like prices and stuff more, and maybe certain protocols that depend on that might get affected, I guess.
Yeah, it's like mostly like addition. A lot of it is like addition bugs. Like one big attack that happened is there's deflationary tokens, and basically every time the token gets traded, a little bit of the amount gets burnt, which means you can mint tokens, which is like, what minting money is, you make more of it. The opposite is you burn. You can like burn tokens out of existence. And the way people do it is they send it to the zero address, because no one will ever have control of the zero address. So if you send money there, it gets burnt. And then, the token contract will reduce the supply too. And so one bug that got taken advantage of is there was a deflationary token. Every time you transferred, it actually transferred a little bit less of the token that was actually there. But this contract didn't think that that would ever happen. And so they were subtracting the total transfer amount, thinking that that's money still existed. Whereas if they had actually queried the data of the token contract and looked at the supply, they would have realized it actually decreased. And so just like a lot of the bugs is you find some addition like wonkiness where the math will start getting off, and then you use that to your advantage to like drain money out of a pool because they think you transferred this amount of money to yourself, but it was actually a little bit less. And so you keep doing that over and over, and this protocol thinks that you have all that difference. And so when the math gets off, they think you have this much money and you don't, you can like pull it out. So a lot of like mathematical discrepancies like that get taken advantage of.
Yeah, that makes sense. Thank you.
Yeah, I wish I could explain it better, but that's what I got. The general gist of how these things happen.
It's a pretty like good explanation, I think, to kind of visualize it a bit.
It's like at a high level, yeah. It's super interesting though, like to every time I'm trying to like actually compile, because I read about attacks and then I kind of move on with my life and I don't chronicle them. So lately I've been actually trying to go back and chronicle all of the ones in like a notebook that I have so that I can consult them later, because it's super useful to know as a developer too. You don't want to make the same mistakes. It's very fascinating.
Yeah, like what stuff to look out for.
Exactly.
So I guess if there's not any more questions, we would kind of end it here. If anyone has any question, last chance.
Yeah. It's a lot. It's a lot to take in.
All right. Well, thank you everyone for coming today.